S, H, F. There are several types of motion. We have linear motion, circular motion, then simple harmonic motion. We are going to treat this into details as we did for linear motion and circular motion. But the question is, what differentiates simple harmonic motion from the remaining types of motion? Now let's look at the various equations under simple harmonic motion. So let's consider this as a simple pendulum ball. So for simple harmonic motion to take place, there should be an oscillating mass. So this ball is the oscillating mass, which is being tied to a string or a thread. We take point, let's take point A as the fixed point of the ball or the mean position of the ball. So these are the keywords: fixed point. Fixed point can also be called mean position. Mean position. So before we displace the oscillating mass, the ball, it should be positioned at its fixed point or its mean position, and that is labeled as A. I now display the oscillating mass or the ball. When you display the oscillating mass, you see the ball moving from the mean position to the extreme end. So let's take this to be one extreme end as the ball oscillates from the mean position, and let's label that let's label that extreme end as P. Now as the ball moves from the mean position to the extreme end, point P, you will see that the ball or the oscillating mass does not stay at point P. It moves back through the mean position to the other extreme end. So the ball will move across the mean position A and get to the other extreme end. And let's label that as Q. So we have 3 points here. Point A, which serves as the mean position or the fixed point when the ball hasn't been displaced yet. Then point P and point Q will serve as the two extreme ends. That's the highest point the ball can reach before coming back to the mean position. But there's a question here we have to answer. If the bulb gets to the extreme end point B, the bulb does not stay there. The bulb stops momentarily and comes back to the mean position. So we can liken this to a body thrown into the air. Whenever you throw a body into the air, the body does not stay in the air. It stops momentarily at its highest point, and force of gravity brings the body back to the ground. So this is telling us that at the mean position P and Q, there is a force there that brings the ball or the oscillating mass back to its mean position A. Now let's look at this. This is the mean position A. Point P is the highest point reached by the ball. So we can also say that this will be the displacement covered by the ball. So if the ball moves from point A to point P, that's the displacement. And let's look at the direct. Don't forget, we have vector quantity and scalar quantities. Vector quantities also shows direction, and displacement is one example of vector quantity. So if from point A to point P is the displacement covered by the ball, then we can also determine the direction of the displacement. So from point A to point P, the displacement will be positive. So we have positive x as the body moves from point A to the extreme end P. Then if the ball moves across point A from point P and it reaches the other extreme end, which is point Q, that one we can also determine the displacement covered by the body. But this time around, the body is moving from the mean position A towards the left, so that we assign negative. So that becomes the displacement. That is what? Negative. Now let's concentrate on this part of the motion as the body moves from the mean position A to point what? P. We've understood that from point A to point P is the displacement covered by the body, and that is what? X. And the direction is from left to right. So that's the direction of the displacement, from left to what? Right. And at the extreme end point P, the body does not stay there. It stops momentarily and moves back. So there is a force here that is causing the body to move back to its main what? Position. And this force is found in the string or the thread that is tied to the ball. And that force is known as a restoring force. So there is a restoring force. There is a restoring force F at point P, so that if the bob gets to point P, it does not stay there. It moves back to the main what? Position. But if the body is moving from P to A, that is in opposite direction to the displacement. The displacement is from point A to point what? P, that is left to what? Right. And the restoring force is causing it to move back to its main position. So this will be the direction of the force. That will be from right to left. This is left to right. So this one will be right to left. So this is telling us that the displacement covered by the ball is in opposite direction to that restoring force, causing the ball to come back to its main position. Now let me take you to second Newton law of motion. You see that we deduce this formula F equals ma. This formula is obtained from Newton's second law. And how do we understand this formula? This formula tells us that whenever there is an applied force, there should be what? Acceleration. In other words, when you see a body accelerating, it means that there is an applied force on that what? Body. So what brings about acceleration is applied what? Force. Acceleration A depends on the applied force what? F. So if the applied force is great, then the acceleration has to be what? Great. Now let's link it to this one. We are saying that the applied force pushes the ball back to the main position, which is in opposite direction to the displacement. In other words, the force will be acting from right to what? Left, as I've indicated here, right to what? Left. And this force will result in acceleration A. So we can also say that the direction of acceleration is also left to right. So that will be the direction of acceleration, left to right. So we can say that the displacement is in opposite direction to the applied force and also in opposite direction to acceleration. So this is the first condition. Whenever a body is undergoing simple harmonic motion, the displacement of the body should be in opposite direction to its acceleration. So that's the first condition. Now let's look at the second one. If the force is moving from right to left so that the ball can come back to its mean position, then we can say that the applied force is being directed towards the mean position. And if acceleration is as a result of the applied force, then we can also say that the acceleration too is directed towards the mean position. So this will be the second condition. The first one is the displacement covered by the ball is in opposite direction to the acceleration. Then the second condition is this: the acceleration, which is as a result of the applied force, will be directed towards the mean position. So these two conditions will give us the definition of simple harmonic motion. Now, how do we define simple harmonic motion? A body is said to undergo simple harmonic motion when its acceleration is directed towards a fixed point, and that acceleration is proportional to the displacement. So these are the conditions for simple harmonic motion. I'm repeating. A body is said to undergo simple harmonic motion when its acceleration is directed towards a fixed point and also directly proportional to the displacement. So this is telling us that the greater the displacement covered by the ball, the higher the restoring force to cause it to move back to its mean position, and the greater the acceleration of the body. I want to put it in a nutshell. If you take this simple harmonic, this simple pendulum ball, as you display or swing the ball from point A to the extreme endpoint P. You see that the ball will moving from A to P, that is left towards right, and that will give the displacement of the ball. But the ball does not stay at point P. So this is telling us there is a restoring force at point P, which pushes the ball back to its mean position. So if the ball is moving back to its mean position, then it is in opposite direction to the displacement. So we can say that the displacement is in opposite direction to the applied force and the acceleration. And this applied force, for you to cause the ball to move back to the mean position, it has to move towards the mean position. So the acceleration too is directed towards the mean position. So these are the two conditions. The acceleration of a body undergoing simple harmonic motion is directly proportional to its displacement. The greater the displacement covered, the higher the restoring force and the greater the acceleration. Then two, the acceleration directed towards a fixed point, which simply means that the acceleration is in opposite direction to the displacement. So these are the two conditions for a body undergoing simple harmonic motion. Pause. These are the conditions. One, the acceleration should be directed towards a fixed point. This simply means that the acceleration is in opposite direction to the displacement. So if the displacement is positive, the acceleration has to be negative. And the second condition, the acceleration is proportional to the displacement. And this condition simply means that the greater the displacement of the body, the higher the restoring force, just to bring the body back to the mean position. And restoring force brings about acceleration. So the acceleration too has to what? Increase as displacement increases. So if you combine these two, you get the definition of simple harmonic motion, which is defined as the acceleration of a body undergoing simple harmonic motion is directly proportional to its displacement and also directed towards a fixed point. Now let's look at equations of simple harmonic motion. Equations of simple harmonic motion. So as we did under linear motion and circular motion, we deduce the equation for the displacement, velocity and acceleration. We are going to do same for simple harmonic motion. Let's stick to the simple pendulum bob diagram. We have this diagram. So point A is the mean position. That's the fixed point. That's where the body will start oscillating. Then let's take this to be the extreme, and that's the highest displacement covered as the body moves from the main position. But if the body gets to this point, it does not stay there. It moves through across the main position and gets to the other extreme end. So we get something like oscillating or back and forth movement of a body from a fixed point. So let's take this to the point Q. And we can liken this to a wave motion. And from a wave motion, the general expression is giving us y equals a sine omega t plus phi. So the displacement of a body undergoing simple harmonic motion is given by x, where x equals a sine omega t plus phi. This x represents the displacement of a body undergoing simple harmonic motion. This A is called amplitude. A is called amplitude. Amplitude simply means the maximum displacement covered. I'm repeating, amplitude refers to the maximum displacement covered by the body. Then we have phi. Phi is the initial phase angle. Initial phase angle. That is phi, initial phase angle. And how do we define phase angle? Phase angle is a fraction of a complete oscillation or a fraction of a complete cycle. If you come back to this diagram, this is the total displacement covered. but it can happen that the body will be found within this path before it gets to the highest point. So the point within a complete cycle is called phase, and the angle formed at that point is known as phase what? Angle. So how do we deduce the formula for a phase angle? From wave motion, the total distance covered by a wave to complete a cycle is called wavelength. That is represented by lambda. So that is wavelength, lambda. And the total angle is what? 2 pi. So we have lambda equals 2 pi. Under wave motion, the total distance covered by a wave to complete a cycle is called wavelength. And a complete cycle has an angle of 2 pi radian. So we can say that wavelength equals 2 pi. That is the total distance, and this is the total what? Angle. So if we are saying that initial phase angle is a fraction of a complete cycle, then it means that the body will be found within that complete cycle. The body hasn't completed the cycle yet. So let's take that distance as x. So we have x equals, that is 5. So we don't know that exact angle. So let's use question what? Mark. So how do we get, okay, let's make it 5. So how do we solve for 5? We cross what? Multiply. So you are going to have lambda 5 equals 2 pi x. So 5 will be equal to 2 pi x on lambda. So this is the formula for initial phase angle, 2 pi x on lambda, which is defined as a fraction of a complete cycle. Let's go back to the formula for displacement of a body undergoing simple harmonic motion. We have x equals a sine omega t plus what? 5. What does this omega represent? We call this angular velocity or angular frequency. And from wave motion or circular motion, the angular velocity omega equals angular displacement, that is theta over time. Angular displacement is theta over time. But we are not going to concentrate on this. We are doing simple harmonic motion. So that's the displacement function for a body undergoing simple harmonic motion. X equals a sine omega t plus 5. Then how do we get the velocity? So let's look at the velocity of simple harmonic motion. Velocity of simple harmonic motion. We all know that velocity is change in displacement over change in time. And from calculus or differentiation, this is small change in the displacement, small change in time, which is also the same as, or which is approximately equal to dx dt for a bigger change. So the x dt means you are going to differentiate the x with respect to what? T. So how do we get the formula for velocity? So velocity has to be the differential of the displacement, that is x, with respect to time. But we all know that the displacement is given as a sine omega t plus 5. A sine omega t plus 5. So we differentiate this with respect to t. So you are going to have velocity equals. So how do we differentiate this? Don't forget, this is, we are going to use product rule. We have two terms here. We have a and sine of this word, function. And how do we use product rule? We are going to hold a constant, then we differentiate the sine with respect to what? T. So if you hold a constant, we get what? A. But don't forget, under trig ratios or under trig, whenever you differentiate sine, you get cos. If you differentiate cos, you get negative sine. So let me give you a small example here. If I differentiate sine x, I will get cos s. If I differentiate sine 2x, I will get cos 2x times the differential of this function. If you differentiate 2x, you get what? 2. So for the sake of those who have not done differentiation yet. This is how to differentiate. If I have y equals x, and I want to differentiate y with respect to it, that is the y dx, it's going to be, you take the power here is 1, so you take the power to multiply the function to be 1 times x. Then you subtract 1 from the power, so it's 1 minus what? 1. So this will give us 1 times x to the power 0. And any number to the power 0 is what? 1. So you get 1 times 1, and that will give you 1. How do you differentiate y equals 2x? Here the power is still what? 1. So it's going to be 1 times 2x. 1 times 2x will give us 2x. Then you subtract 1 from the power, so it will be 1 minus 1. So this will give us 2 times x to the power 0, and x to the power 0 is 1, so you get what? 2. So if you differentiate 2x, you get what? 2. Now let's come back to this. So if I differentiate sine 2x, if you differentiate sine, you get what? Cos of the same function. So sine 2 is the same as cos 2x. Then you multiply by the differential of the function, which is 2x. If you differentiate 2, you get 2. You're going to get 2 cos 2x. So how do we differentiate sine omega t plus 5? If I differentiate sine omega t plus 5, that will give me cos omega t plus 5. So I have cos omega t plus 5. Then I move ahead to differentiate. The term inside the brackets with respect to t. So times. How do you differentiate omega t with respect to t? If you differentiate it, you get what? Omega. So if I multiply it, I'm going to get a omega cos into bracket omega t plus 5. So this is the velocity function for a body undergoing simple harmonic motion. A omega cos omega t plus 5. This is the displacement function, x equals a sine omega t plus 5. Velocity is a omega cos omega t plus 5. Now let's look at that of acceleration. So now we deduce the velocity function as v equals a omega cos omega t plus 5. So for a maximum velocity, omega cos omega t plus 5 should be equal to 1. So you are going to have v equals omega a. So that is the formula for the maximum velocity of a body undergoing simple harmonic motion. Omega times a, where the omega is angular velocity and the a is amplitude. Now let's look at the acceleration. Acceleration of a body undergoing simple harmonic motion. Acceleration of a body undergoing simple harmonic motion. From linear motion, we know that acceleration is change in velocity over change in time. So we are going to differentiate the velocity with respect to time. So acceleration a will be equal to the differential of the velocity. We've obtained the velocity function as a cos a omega cos omega t plus 5. So how do we differentiate this with respect to t? We are going to hold a omega constant, then we differentiate this with respect to t. So we are going to have the differential of the velocity function, which is a omega cos omega t plus 5. If you consider calculus, whenever you differentiate cos, you get negative sign. So here we hold a omega constant. So a omega. Then we differentiate cos of omega t plus 5, and that will give us negative sign omega t plus 5. After that, we multiply by the differential of the term inside the bracket. And if we differentiate with respect to t, we are going to get omega, so times omega. If you multiply through, you are going to get a omega times omega, so omega squared. Then into bracket negative sign omega t plus 5. Let's expand. So you are going to have the acceleration of a body undergoing simple harmonic motion to be equal to negative a omega squared sine into bracket omega t plus 5. For maximum acceleration, sine omega t plus 5 should be equal to 1. So we are going to have A maximum to be equal to negative omega squared A. So this is the formula to get maximum acceleration of a body undergoing simple harmonic motion. Negative omega squared A. The omega is angular velocity. A is what? The maximum displacement covered. But what does the negative represent? Don't forget, when we started, I told you that the acceleration is directed towards a fixed point, which means that it is in opposite direction to the displacement. So the negative here is telling us that the acceleration of a body undergoing simple harmonic motion is directed towards a fixed point. And for a body to undergo simple harmonic motion, its acceleration should obey this equation or this formula. The acceleration should be equal to negative omega squared A. Look at the graphical representation of the displacement of a body undergoing simple harmonic motion. We are going to plot displacement against time. We are going to have displacement, and that is what? Time. You see that we had the displacement function as x equals a sine omega t plus phi. So this is a sine function. So when you draw it graphically, you are going to have this as the graph. So this will be the nature of the graph, where we start from the mean position O. So this is telling us that before you display the oscillating mass or the bulk or the body, it should be at its mean position. At the mean position, you've not displaced the body yet. So its displacement will be 0. That's why from this graph, we are starting from what? 0. And that is giving us a sine function. So this will give us the maximum displacement curve. That's the maximum displacement curve, which is what? The amplitude. But from the diagram that we drew for the simple pendulum, we have something like this, where the body moves the instrument, which is P, from left to what? Right. And we have the displacement to the positive x. Then when it moves towards the left, that is right to left, we have the displacement to be negative. So we have two maximum displacements here. One is positive, and the other one is what? Negative. So there is the graph representation of displacement of a body undergoing simple harmonic motion. Let's look at that of the velocity. So the velocity is going to give us something like this. So we have velocity against time. We had the velocity function as v equals a omega cos into bracket omega t plus phi, and this is a cos function. But the question is, are you going to start from the mean position as we did for the displacement? If you take the simple pendulum ball, at this mean position, the body hasn't been displaced there, so it hasn't covered any displacement. So at the mean position, its displacement is 0. That's why we started from what? 0. But we can't say that the velocity is 0 at the mean position. When you display the body to get to the far end, that's the extreme end point B. At this point, the body has covered maximum displacement. But what happens to the body at this point? It stops for a while momentarily, so its velocity will be what? 0. So at the extreme ends, at the far ends, the body is having maximum displacement, but velocity is what? 0. So where does the body attain velocity? If the body moves back to the mean position, its displacement will be decreasing as velocity what? Increases. At this point, the body stops momentarily, so velocity is what? 0. But when the restoring force pushes the body back to the mean position, that restoring force will cause the body to accelerate, so velocity will be increasing. And at the mean position, the body attains maximum velocity. So the body is having maximum velocity at the mean position. Never forget this. Under simple harmonic motion, the body has 0 displacement at its mean position, the first point. That is when you've not displaced the body yet. When the body gets to the extreme end, it will have maximum displacement, but velocity will be 0. So velocity is 0 at the extreme end, where the body is having maximum displacement. When the body moves back to the mean position, velocity has increased, so the velocity becomes maximum at the mean position. So for a body undergoing simple harmonic motion, its velocity is maximum at its mean position. So velocity is maximum, but at this mean position, displacement is what? 0. So if you want to draw the graph, you don't have to start from the mean position. If you start from the mean position, then you are telling us that velocity is 0 at the mean position, and this is wrong. Velocity is maximum at the mean position. So this is where you are going to start from. So this will give you the graphical representation of the velocity function. The body is having maximum velocity at the mean position, but that same mean position, displacement is what? 0. So this is sine function and this is what? Cos function. Let's look at that of the acceleration. Acceleration. So you are going to plot acceleration against time. Let's go back to the condition for simple harmonic motion. We said that the acceleration is directly proportional to the displacement. So the greater the displacement, the greater the acceleration. And two, acceleration is directed towards a fixed point. And I told you that statement means that acceleration is in opposite direction to the displacement. So if this is the graphical representation of the displacement, starting from the mean position and assuming this shape, the opposite of this, the reverse of this, will give you acceleration. So if we started from here, acceleration should start from here. So there is the graphical representation of acceleration. So it's going to have maximum acceleration at that side. It is in opposite direction. So if this is the displacement, the opposite of this will give you the graphical representation of acceleration for a body undergoing simple harmonic motion.